You know, most people think they understand electricity. They think they know what happens when they flip a light switch. And why shouldn't they? We've been using electricity for over 100 years now. We teach it in schools. We have nice simple diagrams with arrows showing current flowing through wires like water through pipes. It's all very comfortable, very intuitive. But here's the thing that'll really bake your noodle. The electricity, the energy that powers your lights, your computer, everything around you. It doesn't actually flow through the wires. Not really. Not in the way you think. Now, I can see you shaking your head already. You're thinking, Feynman's finally lost it. We've got wires, we've got current, we measure it with ammeters. We can even feel the heat in the wire when too much current flows. How can you possibly say it doesn't flow through the wires? But stick with me here, because what I'm about to tell you is going to change the way you see every electrical device you've ever touched. The energy, the actual energy that does the work, it flows through the space around the wires, through the electromagnetic field. The wires are just there to guide that field, to shape it, to tell it where to go. But the energy itself, it's traveling through the air, through the vacuum, through whatever medium happens to be around the conductor. And this isn't some minor technical detail that only matters to physicists arguing in journals. This is fundamental. This is reality. Let me start with something simple. When you connect a battery to a light bulb with two wires, what do you think is happening? The standard story, the one they tell you in school, goes like this. Electrons in the wire start moving. They're pushed by the electric field created by the battery. They flow from the negative terminal, through the wire, through the filament of the bulb where they give up their energy as heat and light, and then they continue through the other wire back to the positive terminal. Nice and simple. The electrons are like little trucks carrying energy from the battery to the bulb. But that story has a huge problem. Those electrons, they move incredibly slowly. We're talking about maybe a millimeter per second, maybe even slower depending on the wire. At that speed, it would take them hours to get from the battery to the bulb if the wire is even a few meters long. But when you flip the switch, the light comes on essentially instantly, not hours later, instantly. How do you explain that? The answer is that the electrons aren't carrying the energy at all. They're not the trucks. They're more like, imagine a long tube filled with marbles. When you push a marble in at one end, a marble pops out the other end almost immediately, even though the marble you pushed has barely moved. The signal propagates through the system much faster than any individual marble travels. But even that analogy isn't quite right, because it still suggests the energy is somehow in the marbles, in the electrons, and that's not what's happening. What's really happening is this. When you connect the battery, an electromagnetic field appears in the space around the wires. This field appears essentially at the speed of light, not at the speed of the electrons. The field carries energy, and it carries it from the battery to the bulb through the empty space around the wires. The electrons in the wire, they're just responding to this field. They jiggle back and forth. They drift slowly in one direction, and in doing so, they help maintain and shape the field. But they're not the energy carriers. The field is. Now, you might be thinking, okay, that's interesting, but how do we know this is true? How do we know the energy is in the field and not in the wire? Well, let me tell you about something called the Poynting vector. This is a mathematical object named after John Henry Poynting, who figured this out in the 1880s. The Poynting vector tells you the direction and magnitude of energy flow in an electromagnetic field. And here's the kicker. When you calculate the Poynting vector for a simple circuit with a battery and a resistor connected by wires, you find that the energy flows from the battery to the resistor through the space outside the wires, not through the wires themselves. The Poynting vector is given by a very simple formula. It's the cross product of the electric field and the magnetic field divided by a constant. In a wire carrying current, there's a magnetic field circling around the wire and there's an electric field pointing along the wire. When you take the cross product of these two fields, you get a vector pointing radially inward, toward the resistor, perpendicular to the wire. The energy flows in from the sides, from the electromagnetic field in the space around the circuit. Let me give you a concrete example to make this crystal clear. Imagine you have a battery connected to a light bulb with two very long wires, say 100 meters long. You might think, well, the energy has to travel through those 100 meters of wire to get from the battery to the bulb. But calculate the Poynting vector and you'll find something shocking. The energy actually takes a shortcut. It flows through the space between the two wires, almost directly from the battery to the bulb. The wires are just there to set up the field configuration that guides the energy flow. Now, here's where it gets even more disturbing. Imagine you could somehow make a circuit where the wires go in a really roundabout way. Maybe they loop around several times before reaching the bulb. The electrons would have to follow that entire path. But the energy could flow through the field almost directly from source to load, cutting across all those loops. The path of the energy and the path of the electrons can be completely different. I know this sounds crazy. It sounds like I'm playing word games, like I'm making distinctions without differences. But this is absolutely real, and it has real consequences. Let me give you an example. There's a thought experiment, sometimes called the Feynman disk paradox, though there are variations of it. Here's the setup. You have a solenoid, a coil of wire, and you have a disk with charges on it. The solenoid creates a magnetic field, and when you turn off the current in the solenoid, the changing magnetic field creates an electric field. This electric field exerts a force on the charges in the disk, and the disk starts to spin. Now here's the question. Where did the angular momentum come from? The magnetic field of the solenoid was pointing straight up through the disk. There was no obvious rotation anywhere, but when the disk starts spinning, angular momentum has to be conserved. It had to come from somewhere. The answer is that the angular momentum was stored in the electromagnetic field all along. There's something called electromagnetic momentum, and it exists in the field whenever you have crossed electric and magnetic fields. The Poynting vector is actually proportional to this momentum density. When the fields change, that momentum can be transferred to matter, making things move. This isn't abstract theory. This is real. You can do experiments that demonstrate this. The electromagnetic field carries energy. It carries momentum. It can even carry angular momentum. It's as real as any material substance. In fact, in a very deep sense, it's more fundamental than matter. Matter is just a particular configuration of fields, when you get right down to it. The electrons in your wire, they're excitations in the electron field. The photons of light, they're excitations in the electromagnetic field. Fields are what's real. Particles are just a useful way of talking about certain behaviors of fields. But let's get back to wires and circuits, because I want to make sure you really understand this. When current flows through a wire, the wire does heat up. That's real. The electrons are colliding with the atoms in the wire, transferring energy to them, making them vibrate more, which we perceive as heat. So the electrons are doing something. But where did they get that energy? Not from some internal battery of electron energy. They got it from the electromagnetic field surrounding them. The field pushes on the electrons move, and in moving through the resistance of the wire, they give up energy as heat. But the ultimate source of that energy is the field. Think about it this way. Imagine you have a water wheel in a stream. The wheel turns because the water pushes on it. Where does the energy come from? From the water, you'd say. But where did the water get its energy? From gravity pulling it downhill. The water is just the medium that carries the energy from the gravitational field to the wheel. In an electrical circuit, the electrons are like the water. They're the medium. The electromagnetic field is like gravity. It's the real source of energy. Here's another way to see it. Light is an electromagnetic wave, right? It's an oscillating electric and magnetic field propagating through space. And light carries energy. We know this. Sunlight warms your skin. A laser can cut through metal. That energy is in the electromagnetic field of the light wave. There are no electrons in a light beam traveling through vacuum. The energy is purely in the field. Now, in a wire, you have a very similar situation. You have electric and magnetic fields, and they're carrying energy. The only difference is that in a wire circuit, the fields are guided and shaped by the presence of conductors, and there happen to be electrons around that respond to the fields. But fundamentally, the energy transport mechanism is the same. It's the electromagnetic field doing the work. Now, I want to address something that might be bothering you. If the energy flows through the space around the wires, why do we even need wires? Why can't we just send energy through the air without wires? Well, the answer is that we can, and we do. That's exactly what radio waves are. That's what Wi-Fi is. That's what all wireless communication is. We're sending electromagnetic energy through space without wires. The difference is one of efficiency and control. With wires, we can guide the electromagnetic field very precisely to where we want it to go, and we can do it with very little loss. Without wires, the field spreads out in all directions, and most of the energy goes where we don't want it. But here's something really interesting. Even with wires, some of the energy leaks out into the surrounding space as radiation. This happens especially when you have alternating current, when the fields are changing rapidly. High-frequency signals, like the ones in your computer or your phone, they radiate. That's why electronic devices have to be shielded, why there are regulations about electromagnetic interference. The energy isn't perfectly confined to the region around the wires. Some of it escapes and propagates away as electromagnetic waves. Let me tell you about another phenomenon that makes this even clearer. Transmission lines. When you need to send electrical signals over long distances, especially high-frequency signals, you can't just use any old wire. You need carefully designed transmission lines, coaxial cables, twin-lead wires, microstrip lines on circuit boards. These are all transmission lines, and they're designed to control the electromagnetic field pattern around the conductors. In a coaxial cable, you have a central conductor surrounded by an insulator and then an outer conductor. The electromagnetic field exists in the insulator between the inner and outer conductors. That's where the energy flows. The geometry of the cable is carefully chosen to make the field pattern clean and to prevent radiation. The impedance of the cable, how much it resists the flow of energy, depends entirely on the geometry of the space between the conductors. It doesn't depend much at all on what metal the conductors are made of, as long as it's a good conductor, because the energy isn't flowing in the metal, it's flowing in the space between the metals. You can do experiments with transmission lines that make this absolutely undeniable. One of my favorites is this. Take a coaxial cable and cut the center conductor, just slice it right through so there's a gap. Now, what do you think happens when you send a signal down that cable? You might think, well, the circuit is broken, the electrons can't flow across the gap, so the signal can't get through. But that's wrong. If the gap is small enough, the signal goes right across. How? Because the signal isn't electrons flowing through the conductor. It's an electromagnetic wave propagating through the insulator. The wave can jump the gap just fine, as long as the gap is small compared to the wavelength. In fact, you can make a capacitor this way. Two conductors separated by an insulator with a gap. For DC, for steady current, this blocks the flow of electrons. But for AC, for alternating current, the electromagnetic field can oscillate across the gap and energy flows right through. No electrons cross the gap, but energy does. If energy were really flowing through the electrons through the conductor material, this would be impossible. Now let's talk about something that really drove this home for me when I was first learning about this stuff. Superconductors. In a superconductor, electrons can flow without any resistance at all. You'd think this would be the perfect case of electrons carrying energy efficiently. But here's the thing. In a superconductor, the electrons pair up in a very special quantum state, and these pairs move through the material without scattering. But when you calculate where the energy is, you still find that it's in the electromagnetic field around the superconductor, not in the electrons themselves. In fact, there's a beautiful effect called the Meissner effect. When a material becomes superconducting, it expels magnetic fields from its interior. The magnetic field gets pushed to the surface of the superconductor. Why? Because the superconducting electrons create currents that perfectly cancel the applied magnetic field inside the material. The field, the electromagnetic field, exists only in a thin layer at the surface and in the space outside the superconductor. And that's where the energy is. Even in the ultimate case of perfect conductivity, the energy is in the field, not in the material. Let me give you one more example, and this one is really beautiful. Waveguides. These are hollow metal tubes used to guide electromagnetic waves, especially microwaves. There's no center conductor. It's just an empty metal tube. Electromagnetic waves propagate down the tube, bouncing off the walls. The energy flows through the empty space inside the tube. There are electrons in the metal walls, and they respond to the fields, creating surface currents that reflect the wave and keep it confined. But the energy is in the wave, in the field, in the empty space, not in the walls. You can even have something called a cutoff frequency in a waveguide. Below a certain frequency, waves can't propagate through the tube at all. The geometry just doesn't support it. Above that frequency, waves propagate just fine. This has nothing to do with the conductivity of the metal. It's purely about the geometry of the space and how electromagnetic fields can exist in that space. If energy were really flowing through the metal, this frequency dependence wouldn't make any sense. So, where does this leave us? It leaves us with a picture of electricity that's very different from the simple models we start with. Current in a wire isn't like water in a pipe. It's more like the electromagnetic field around the wire is a highway, and the energy is flowing along that highway. The electrons in the wire are like guardrails or lane markers. They shape the highway. They keep the field organized, but they're not the cars carrying the cargo. And this isn't just some philosophical point. It matters for practical engineering. When you're designing high-speed circuits, when you're working with radio frequency signals, when you're trying to minimize electromagnetic interference, you have to think about the fields, not just the currents. You have to think about where the energy is actually flowing. Circuit board designers have to carefully control the geometry of traces and ground planes to control the electromagnetic field patterns. Antenna designers have to shape the fields to radiate efficiently in desired directions. Even at lower frequencies, even in ordinary household circuits, this perspective helps explain phenomena that are otherwise mysterious. Why does a power cord radiate electromagnetic waves that can interfere with radio reception? Because some of the energy in the electromagnetic field around the cord leaks out as radiation. Why do some cables pick up noise while others don't? Because they're allowing electromagnetic fields from the environment to penetrate and induce currents. It's all about the fields. Now, I know some of you are still resisting this. You're thinking, but I can measure the current in the wire. I can measure the voltage. I can use Ohm's law. And it all works just fine without worrying about fields in space. And you're right, you can. For many purposes, the simple circuit theory works perfectly well. And that's because circuit theory is an approximation, a very good approximation for low frequencies and compact circuits that captures the essential behavior without having to solve the full electromagnetic field equations. But it's an approximation. The deeper reality is that Maxwell's equations govern everything electromagnetic, and Maxwell's equations are all about fields. Current and voltage are useful concepts derived from the fields. Current is related to the magnetic field circling a wire. Voltage is the integral of the electric field along a path. These are shortcuts, ways of talking about field behavior without having to track the fields everywhere in space. They work when the circuit is small compared to the wavelength of the signals involved, when the energy has time to redistribute itself into equilibrium patterns. But when circuits get fast, when they get large, when frequencies get high, the approximations break down and you have to face the full field theory. And here's the kicker. Even when the approximations work, even when circuit theory gives you the right answer, the energy is still flowing through the fields. The math of circuit theory is set up to give you the right answer without tracking the field explicitly, but nature doesn't care about our mathematical convenience. Nature does what nature does, and what nature does is move energy through electromagnetic fields. Let me tell you why I find this so beautiful. It unifies everything. Light, radio waves, electrical circuits, all of it is the same phenomenon. Electromagnetic fields carrying energy through space. The only difference is the frequency, the geometry, the boundary conditions. A wire guiding energy to a light bulb and a fiber optic cable guiding light to your computer are doing essentially the same thing. They're shaping electromagnetic field patterns to direct energy flow. There's a deep unity there, a simplicity underneath the apparent complexity. And it ties into quantum mechanics too. When we quantize the electromagnetic field, we get photons. And photons carry energy and momentum. A photon traveling through empty space is a quantum of the electromagnetic field. But even in a circuit, even with DC current, the energy is in the electromagnetic field. And if you were to quantize it carefully, you'd find it's made of photons too, just very low energy ones, huge numbers of them, so many that the quantum nature washes out and it looks classical. But fundamentally, it's the same thing. This also helps explain why the speed of signals in circuits is limited by the speed of light. The electromagnetic field changes propagate at the speed of light, or rather at some fraction of the speed of light determined by the medium around the wires. When you flip a switch, the information that the switch has been flipped travels along the wire as a change in the electromagnetic field, and that change propagates at this wave speed. The electrons barely move in the time it takes for the light to come on. They couldn't possibly be carrying the information. The field carries it. You know, when I first really understood this, it bothered me for a while. It felt like I'd been lied to. All those years of learning about circuits, about current and voltage and resistance, and nobody told me that the energy isn't even in the wire. But then I realized, no, it wasn't a lie. It was a simplification, a very useful one. You don't teach kids about quantum mechanics before you teach them Newtonian physics, even though we know quantum mechanics is more fundamental. You start with the approximation that works in the regime you care about, and you build up from there. But at some point, you have to face the deeper truth. And the deeper truth about electricity is this. The wires are guides, not carriers. The electrons are responders, not transporters. The electromagnetic field is where the action is. That's where the energy lives, where it flows, where it does its work. Everything else is just a consequence of that fundamental fact. And once you see it this way, you can't unsee it. Every time you turn on a light, you're not sending electricity through a wire, you're creating an electromagnetic field configuration that channels energy from your power source to your bulb through the space around the wires. Every time you charge your phone, Energy flows through the air in the charging cable, guided by the conductors but not traveling through them. It's happening all around you, all the time. This invisible ocean of electromagnetic fields carrying energy from place to place. That's what makes physics beautiful. It takes the familiar and shows you that it's strange. It takes the obvious and reveals that it's subtle. Electricity doesn't flow through wires. It flows around them, through them, in the space where you thought there was nothing. And that nothing, that empty space, is alive with fields, with energy, with the fundamental forces that make our technological world possible. That's the reality. That's what's really going on, and I think that's absolutely wonderful.